Well then, all right, it is lesson 7 in unit 1, and lesson 7 is all about continuity. What does it mean for a function to be continuous? Why does continuity matter? Why is it valuable to us? And so, I mean, we all know what continuity is intuitively. Intuitively, we mean that a function is continuous if you can draw it without picking up your pen from the paper. That's how we know that a function is continuous. If at any point you have to pick your pen up from the paper because there's a hole in the function, or you have to pick your pen up from the paper because the function jumps from here to there, or you have to pick your pen up from the paper because I should go purple here, but I can't. Can I? I can. Because there's some kind of serious oscillation happening in there, and it's going so fast that you can't really deal with it. Those are cases where we know, okay, intuitively, those functions are not continuous. So if I can, I'd like to bring a definition to continuity, and then we're going to go back to that other slide, and we're going to talk about why those other functions are not continuous. A function, y equals f of x, is continuous at an interior point of its domain. We're going to call that point C. C is the x value of an interior point of the domain. Not talking about the endpoints of a domain, just the interior points. If the limit as x approaches C of f of x is f of C. In other words, this thing has to exist. It has to exist. You have to be able to say, okay, as I approach this particular x value, there is a limit. The function is getting closer and closer to some number. This has to exist. The function actually has to be defined at C, and then those two things have to match. So it's really a three-part definition. The limit as x approaches C has to exist, the function value has to exist, and they have to match. Now, obviously, if the domain is a closed interval and you're looking at the left endpoint, then we're not looking at the limit as x approaches C. We're only looking at the limit as x approaches C from the right. And obviously, if we're looking at a function, I'll just draw it really quick so you can see what I'm talking about. If we're looking at this function, then as we approach the right endpoint, we're not looking at the limit as x approaches the right endpoint. We're looking at the limit as x approaches the right endpoint from the left side, because that's all we've got. So, okay, there we go. So back to that other slide. Why is the red function discontinuous? Well, here's my point C. Does the limit as x approaches C exist? Sure it does. Does the function exist there? No. And even if the function existed here, then we would have a limit and a function value, but they wouldn't match. And so in a case like this, we have what's called a point discontinuity. In a point discontinuity, the limit as x approaches C is different than the function value, either because that function value doesn't exist or because it is some other number than the limit. Why is the blue function discontinuous? Well, clearly, f of C, I just picked up green. Really, folks at home? Really? F of C clearly exists, but, so f of C exists, but the limit as x approaches C doesn't. there is no limit as x approaches c. And so that we have some break in the function. In fact, it looks like the function jumps from one branch to another. And so this is in fact called a jump discontinuity, because there is no limit as x approaches c. This is very, very common in any function defined piecewise. So when you see functions that are defined piecewise, your radar goes up. You're saying this could be a jump discontinuity. And then there are functions like this one. This is one of my favorites. This is called an oscillating discontinuity. And you're going to have to do this in the privacy of your own home. You're just going to have to give it a go. That's a graph of sine of 1 over x. And what I want you to do in the privacy of your own home is I want you to keep the y values from -1 to 1, because that's what a sine graph is. But look at smaller and smaller and smaller intervals around x equals 0. Look at -1 to 1, then -0.1 to 0.1, then -0.01 to 0.01. And what you will see is that this function oscillates so wildly as x gets closer and closer to 0 that the limit as x approaches 0 does not exist, not even close. Not even close. A little bit of vocabulary. A point discontinuity is called removable. And it's called removable because if we were to redefine the function in such a way that plugs up the hole, and it doesn't take much, it takes one small change, then the function would be continuous. That, in fact, is called a continuous extension of this function. Not so much with this one. This is a troublemaker, but this one has a removable discontinuity because, here, off screen, that's a removable discontinuity because all you have to do is stick your finger in that hole there, plug up the hole in the dam, and we're okay again. Jump discontinuities and oscillating discontinuities are called non-removable. And they're called non-removable because you can't just simply solve the problem. There's a serious gap in the blue function. There are serious issues on the purple function. So those functions have what we call non-removable discontinuities. Okay, so here's the big deal with that, because you may well ask, who cares? Well, I mean, on the upside, we like functions that behave well. So, I mean, that's a nice side note. We like functions that behave well. Continuous functions behave well. When we add two continuous functions, we get a continuous function. When we multiply two continuous functions, we get a continuous function. And so polynomials are continuous, beautiful things like that. But what we really care about is this thing called the intermediate value theorem. I mean, aside from the fact that you're going to have to answer questions about the definition of continuity on the test in May, one of the largest upsides of continuity is this idea called the intermediate value theorem, and it sounds like this. A function y equals f of x that is continuous on the closed interval AB takes on every value between f of A and f of B. Takes on every value between f of A and f of B. So if I have a continuous function on a closed interval from A to B, I know that every y value in this green band, every y value in this green band gets hit at least once, maybe more than once, between A and B. At least once, possibly more than once. So again, go ahead, ask the question, who cares? Well, oh. That's why we care. Show that that polynomial equation has at least one root. And so what do you do as a student? You go to your calculator and you graph this thing, and you look for, you graph x cubed minus x plus 2, and you say that has to have a 0. And since that has to have a 0, because the directions say it does, I go x cubed minus x plus 2 equals 0, and I sketch a graph, and I say, it's got to have a root. Look, it has a root right here. And then how do you find that root? You say, okay, I want to find a 0, and then I have to shimmy over here where the cursor is at a negative y value. And then I have to shimmy over here where the cursor has a positive y value, and I take a guess that really is just Texas talk, and there it is. What happens there? I'm going to pull this thing in so that you can see what happens. Oh, there's the sound. Here's what happens. You find some place where the function is negative, and then you find some place where the function is positive. Your calculator assumes that anything you're graphing is continuous. And since your calculator assumes that anything you're graphing is continuous, if you give the calculator one place where the function is negative and one place where the function is positive, the intermediate value theorem says that that function has to take on every possible y value between the first y value and the second y value, which means it has to take on 0 because 0 is in between the negative number and the positive number. So your calculator uses the intermediate value theorem with the guarantee that there has to be a root to a continuous function between a negative y value and a positive y value. And then what your calculator does is a variety of algorithms that help it identify where that root is. But your calculator can't even get started if the intermediate value theorem isn't true. So how do we show that? We say, well, it's pretty obvious that f of 0 is 2, where this is f of x. And it's pretty obvious that f of negative 2 is negative 4. And so we would write something like, so f of x takes on all y values between negative 4 and 2, specifically 0. Because f of x takes on all those y values, it takes on 0. Because of that, since f of x is continuous, and the intermediate value theorem holds, f of x equals 0 somewhere on negative 2 to 0. Now the downside is we don't know where it hits between negative 2 and 0, but we know that it hits at least once. Could hit more than once, but we don't care because we're just looking to find that it has at least one root, and we have done the job. Okay, so I'll have more examples for us when we get to class about how to find removable discontinuities and non-removable discontinuities and how to know which is which. But those are the highlights, the broad strokes, and I hope they were good.